Actually, I'm going to pin. Oh, view, hang on. Admit all, just admitting. Okay, hold on. And then what I want to do, I want to pin me and then do that. Okay. I don't know where to put myself now. Okay, so I might have to move me around just so I can look at you. So, yes, I was chatting to one of my students this week about practicals and the 5 critical things you must remember whenever there's a question on required practicals. Remember the 5 things. So, first one, identify your independent variable straight away. It's the one and only thing you will be changing. Number 2, identify the dependent variable. So that's the thing you're measuring. So it could be time, it just could be temperature. I don't know, anything really, but it's the one thing you're going to measure. The third thing are your control variables. So this is making sure your volumes of water, not amount. Try not to write amount. You will still get marks, but it's not as accurate. So it's your mass of an object, it's the volume of a liquid. They all must stay the same: temperature, pH, concentrations, all those things must stay the same, apart from the thing you're independent, okay? And then the fourth thing is your control. Hang on, hold on. With your control, it is the whole of the practical, but without the absence of maybe like a stain or a certain thing that you're adding. Okay, so do not get confused between a control and a control variable. They are completely different. Control variables are what you've got to keep the same. Control is something what you're comparing, so you know it is what is the independent variable that is causing the results. Okay, and the last one, they will always ask about making it reliable. Making it reliable, you need to repeat it at least 3 times to calculate an average. Okay, and if you want to make it more accurate, you need to therefore pinpoint or narrow the range of the independent variable. For example, narrow the pH range or narrow the temperature. Okay, so there's a few, maybe 6 there, but those are the main 5. So independent, dependent, control variables, your control, and how to make it reliable. Okay, when you're reading the question, highlight those, or if they're asking you to design an experiment, they're the 5 things you focus on. Okay, right. Anyway, so there, 4 practicals. Can't remember now. I think there's 4, but 1 for separate sciences as well. So the first one, which I think even like year 9s have done now, possibly, is you're making a salt. It's going to be from a carbonate or an oxide. Now, I have summarized this on 2 sides because it's not, it's a bit too much. So there's key things on here. So a salt is an ionic substance. So we have already covered ionic bonding, things like that in the 2nd module. Some year 10s you would know that, year 9s you're getting onto that. Soluble and insoluble, know the difference. This is also in your separating techniques. Soluble is when it mixes. Always think of that as salt and water. Separate that with evaporation. Insoluble, it doesn't dissolve. So think like sand and water, that sort of thing. Okay, so know those words. What is the point of the practical? So this, the point is to make a dry sample of soluble salt from an insoluble carbonate or oxide. Okay, some science behind it. These are sort of really key bits for this topic that you need to remember. You need to know how acids and metals react. There's 4 main equations. Okay, they all produce salts. Okay, but there's either hydrogen if it's just a metal, water because you've got H2O. Yeah, if you've got metal oxide, that's got oxygen, so it makes water into the hydrogen. Metal hydroxide, you've got OH on there, water again. And a carbonate's got another carbon in it, so you actually produce water and carbon dioxide. Okay, and there's some examples there. And the second bit that's really important is you've got 3 main acids for this, well, that you will be learning about for GCSE. You need to know the name of the salt depending on the acid you use. So if it's hydrochloric acid, the chlorine will attach to the metal and form a chloride salt. If it's nitric acid, it will form a nitrate salt, and if it's sulfuric acid, it'll be a sulfate salt. Now, these are just little extra ones. Ethanoic acid is actually vinegar as well, but you get the idea. But the top three there are the main ones you've just got to remember. So they might ask you if it reacts hydrochloric acid with sodium, what salt do you get? You have to name it, and it's sodium chloride. Okay. What may they ask you about? How do you get solid crystals from salt solution? So this actually is called crystallize or crystallization, where you have to evaporate the water. Why do we heat the solution? That helps with dissolving and reacting the insoluble carbonate or oxide. That's really important. Risks, they often ask about risks. You don't overheat it. And acid is always harmful, or irritant, should I say. Copper oxide is also harmful. Another little question, why do we filter the solution? So once you've added the carbonate or oxide to the acid, you have to keep going until you see black bits floating around. So that is actually leftover carbon, the carbonate or oxide that hasn't dissolved. It's like with salt. If you add so much salt to water, it actually forms at the bottom because it becomes saturated. And what we're doing is we're putting so much metal or metal oxide, etc., in there that all of the acid reacts. And obviously, if an acid runs out in the reaction, there's no reaction. So then filtering just removes that excess. How do we test the pH for the salt solution? Just use universal indicator or paper, that sort of thing. A salt will always be neutral. Okay, salt is neutral. Name the salt produced, that's why I've added that there. Okay, some little background information. Hello, click, click, click. So I've also added some little diagrams here. Let me move me out the way. So you're more likely have done this one here, the acid and metal, and in the video, this is the method you use. So mixing it, it's a nice black substance, a carbonate. You heat it gently, don't forget, and then you filter it and then evaporate it. So that's the process. And then with the carbonate, you get carbon dioxide produced, and you test it with lime water. They might ask you, how do you test that, what the gas is that's given off, and it's carbon, you bubble it through lime water, and that's will go cloudy if there's carbon dioxide. Remember, it's one of your basic tests, along with oxygen, hydrogen, and chlorine. You need to know how to test for those basic gases because they are all colourless and odourless. Or actually, chlorine isn't. Chlorine's a bit greeny. Please don't inhale it or anything because it's very toxic as well. How do we hit? Oh, we've just done those ones. I've added that twice on there. That's my mistake there. But I've done a little diagrams and things like that. So they're the main typical questions that they will ask, like why does it get heated? What's your safety precautions? What's the acid? What's the salt produced? Name the salt, etc. Okay, but they're your typical questions for that one thing. And don't forget about the equations. You might have to write out the equation and what the products are. So remember, hydrogen, water, or carbon dioxide are the other products. Okay. The second one, electrolysis. Now I've gone a bit overboard with this one because electrolysis, it doesn't need to be that complicated. Hang on, bear with. How do you go from how do you go from hydrochloric acid to sodium chloride? So that, hang on, let me go back. Go back. How do I go back? They're going to let me go back? I doubt it. Oh, hang on, let me draw on this one. So you've got, has it got hydrochloric acid? Can I annotate? Bear with, annotate. So here, for example, you've got hydrochloric acid. You mix it with a metal, and what happens? You've got your hydrogen and chlorine. So that's your hydrochloric acid and your magnesium. And what happens is the chlorine binds with the metal, to form metal magnesium chloride, and then you have your hydrogen. So my pen doesn't really work. Release as well. So the hydrogen, it becomes free, and the chlorine binds with the metal. So that's how you get your. That's how it goes from hydrochloric acid. This isn't a complete equation. It's just showing what the acid is in the reactants, and therefore what would the products be. Okay, so this bit down the bottom here isn't a full equation. It's just a summary of the names. Is that okay? I need to clear all drawings. I hope that has answered that one. I want to delete that. Brilliant. Excellent. Hang on, I've got to now click on that to go through. Right, electrolysis. I'm hoping this gives a nice little summary of the main points of electrolysis and things to point out. There is a required practical on this, and that's all to do with aluminium. Okay, but the main point of the practical is to use electrolysis to separate metals from their ores. Now, ores are what we call the metal's natural, I don't know, compound, I suppose, that's found in the earth. So we extract it from the earth, and then we have to separate it. So it might be magnesium oxide in the earth, for example, and we need to get the oxygen off the magnesium, for example, and then we get our metal. So this technique is used for the most reactive metals in your reactivity series. So that's like magnesium, potassium, etc. And we also do it, well, it says to identify products of electrolysis. So that is always the tricky one. So I have a nice little summary table of that and how it all works. But the main bit is there are kind of like 3 parts to electrolysis that they will test you on. The first bit is your basic electrolysis. So they'll give you an example of a single substance. Yeah, it won't be that one. It might be lead bromide, for example. So it's not a solution. It is just the pure lead bromide. So therefore, it is again to do with ionic bonding. Okay. It's a metal with a non-metal, and it's the metal is a positive charge and the non-metal is a negative charge. And we need to separate those out, and we do that through electrolysis. Okay. You have to remember how the apparatus is set up. You have to remember it's a circuit. At the moment, when you stick the electrodes in, your negative one is called cathode and your positive one is anode. It is not a complete circuit until you put the electrolyte, which is the solution, into the container. And it's conductivity of electricity. The principle is that electricity will pass through something or a solution if you have free mobile ions. Okay, if the ions are fixed together in a solid, they're not moving, and therefore the electricity cannot pass through. If you stick 2 electrodes into salt, like table salt, it will not, the electricity will not pass through, the bulb will not come on. If you dissolve salt into water and make a solution, the ions that are then mobile, they're moving around in the water, will then enable the electrolysis or electricity to pass through, and the bulb comes on. Okay, so remember, if it's solid, it will not conduct electricity because there's no mobile ions. Okay, so there's the first situation was when you just got a single compound like lead bromide. The second situation for electrolysis is when you've got a solution. So that's just a little bit more challenging because you've got water involved as well now. So not only have you got your metal and non-metal, but you've got water that breaks down into hydrogen, positive hydrogen here, and negative OH. So this is your hydroxide ions. Okay. And then the third type of question you'll get for electrolysis is about the required practical, the aluminium. Okay, so I'm going to break down electrolysis into really simple things that you have to remember. Okay, it is based on like pretty much your first 2 modules. So your first module is all about atoms and the electrons around the edge, and in that first module you talk about how atoms get converted to ions. That's through loss or a gain of electrons, and therefore you produce a charged atom, which is an ion. In electrolysis, it's the reverse. You have these charged elements, for example, sodium and chlorine. And what's happening, you're obviously creating a current because they are ions and they're positive and negative charge. So the negative will always be attracted to the positive, and the positive ion will always be attracted to the negative. And then at those electrodes, what's happening is either the atom is getting rid of the electron that it's gained to become an ion, or it is gaining back the electron that it's given away to form an ion. So it's actually a reversal. So you've gone from an atom to an ion, and now in electrolysis, you're going from an ion to an atom. So where metals, which are in group 1 and 2, they will lose their electron to become an ion. What happens is they bring back, they gain that electron. And then at the at the positive electrode, the anode, the non-metals get attracted because they are negative, and therefore they give away that electron that they've gained, and then they become atoms again. So that is the basics of what's happening in electrolysis. Okay, so I'll highlight this one. Yeah, so I've kind of summarized that here. So what happens when the positive, this is the typical question, what happens when the positive ion gets to the negative electrode? That it is, all you've got to say is that they are, here we go, reduced or oxidized. So at the negative electrode, it always gets attracted, the positives always get attracted, and the positives are always metals, okay? And then they, have I done that right? Yeah. So they gain an electron to become an atom again. So they are reduced. So remember, metals attracted to the negative, and they are reduced because they gain electrons. Okay, so a non-metal is always negative. It gets attracted to the positive electrode, and it loses an electron. It gives that electron to the anode then, and it's oxidized. Okay, that's the simplicity of it. The questions will ask you which one's the positive, which one's the negative ion, and the metal's always positive, the non-metal's always negative, and then they'll ask which electrode will it get attracted to. Anything opposites attract. Okay, so that's kind of what I highlighted here. Half equations. Don't know what, yeah, people get so confused with half equations. So I have put a little diagram here, down here, about half equations. So what I have described is what we call a half equation. Okay, so let me just show you here. I'm annotating. So the anode is your positive electrode. So it's going to attract the negative chlorine. Sorry, it's a bit small there, but I couldn't enlarge it anymore. So you have to identify whether it is a diatomic. Does anybody not know what diatomic is and how to identify diatomic elements? Because if you don't, oh. Okay, so I don't know if everyone's got a periodic table in front of them. Okay, but all you've got to remember for diatomic elements, you've just got to remember the number 7. Okay, because there are 7 diatomic elements, and these are mainly in group 7 on the periodic table. So it's actually group 7, and it goes from fluorine down to iodine. Oh, so all of these are diatomic, and diatomic means that they go around in pairs, basically. But that's only 1, 2, 3, 4 of them there. Now, there's also 2 more on that right-hand side, nitrogen and oxygen. And if you look on the periodic table, you will see that nitrogen, oxygen is in group 5, 6, and then you've got 7, group 7, that goes down. So if you look at it, it actually looks like a number 7 as well. Okay, so there's 7 elements, mainly in group 7, looks like a number 7 as well with nitrogen and oxygen. The only unique, because it's always in science, always a unique special one, is your hydrogen. Okay, hydrogen it either gets put right in the middle of a periodic table, like above the transition metals, just because it's no specific place, or at the top of group 1 because it's got 1 electron in its outer shell. But hydrogen is the exception to the rules, but that's it. So that's a nice little way to remember which ones are diatomic, and it's really important for this practical to remember and to just right, is that a diatomic element, yes or no? Okay, so always double check. So chlorine is a diatomic, and that is quite a commonly used example in an exam question. So there's all these chlorines going around, they're all negative. Oh, my pen works. Okay, so if we think about a chlorine has an extra negative, extra electron, because it has gained it from its ionic bonding. So what it's going to do, it's going to lose it, plus an electron, to become an atom again. But chlorines are diatomic, they have to go around in pairs. So actually 2 chlorines, oh my goodness, I put that in the wrong place. Erase, thank you. And now deleted that bit. So chlorine is diatomic, so it goes down in pairs. So we need 2 chlorines to bond together. They both release an electron, so 2 electrons get released as well. And sorry, it hadn't done that arrow then. So these are non-metals, and they always happen at the anode. Okay, and this is called, when it loses, I think this is always oxidation. Oxidation. I need to get a new pen. So what's happening at the cathode is negative, so it attracts the metal, which is always positive. And what happens here, that positive metal, in this case sodium, is in group 1, so it should have that 1 electron in its outer shell. So all it needs is an extra little electron that it gets from the electrode, and then it forms just an atom. So it goes from an ion to an atom. So it's the reverse of ionization, basically. And ionization is when an atom turns into an ion. So that's also links to radioactivity module. Okay. So that's your half equations. Okay. The other thing you've got to remember, like I've done with chlorine here, you have to balance the equation. Wherever you go, if you see an equation, just always check it's balanced. Really important, especially when you come to like neutralization, titration, practical. Okay. So that is an example of what's happening with the positive and negative. So if we build on that, when a substance like sodium chloride, which is salt, is added with water, we not only have our negative chlorine and our positive sodium, but with water, when it's a solution, so identify that word solution here in the question. As soon as it says solution, there's water involved as well. So you have to consider positive hydrogens. So your 2 positive ions here will get attracted to the negative. And then your 2 negatives, which will be your chlorine, and this is your hydroxide ion, will get attracted to the positive. Now, there are rules to which ones actually gain or lose electrons. So that's what we're going to come to in a minute. Okay, but the same principles arise. You've got to think about the half equations. Which elements are going to be attracted there? Are they going to gain or lose an electron? And that's how you write your half equations. Okay, let me clear that, get that, and then I'll go on to the second page. So yeah, I've detailed here a little bit more about your substances in solution. There's a little bit here that I was going to mention. Right, let me move my bar out of the way. So for it, a very, very common solution is your sodium chloride. Okay, that's your salt. So it forms positive sodium, negative chlorines, but then you've also got water and hydroxide as well. So in this situation here, which we'll talk about in a minute, your hydrogen, this is your gas that bubbles off, H2. And here you've got chlorine here, chlorine here, which is also a gas that bubbles off there. And then they'll ask you as well, how do you test for these? So hydrogen will be your squeaky pop test. Okay, you might need to put a test tube over the top here or something. Sometimes you might see it. Oh, it's really bad drawing. A design where there's test tubes and you collect the gas given off, and then you've got to test it. So make sure you know what hydrogen, squeaky pop test, chlorine, it will bleach your litmus paper because it's a halogen, and it's that's what their properties are. They bleach things. But that leaves 2 ions floating around in the liquid. So what is left is your sodium and your hydroxide. Okay, and they actually join together, a single positive sodium and a single negative hydroxide to form sodium hydroxide. Now, all hydroxides are alkaline. Okay, so that's really important, especially in neutralization. A hydroxide is alkali, so its pH will be between 8 and 14. And if you add a little bit of universal indicator to that solution, it will go a nice sort of purpley color. Okay, so that might also be asked. So what color? Well, not only will be how do you identify the gases given off, but it might also ask, well, how do you identify the pH in the remaining electrolyte? So the solution is always called the electrolyte. Okay. Now, rules for ionic solutions. So sodium chloride is an example of ionic solutions. And what you've got to do here is think about the anode and the cathode separately. So the anode is positive and it will attract your negative. So that would be typically your halogens, your non-metals, and it would your negatives could be, the halogens, which is here. These pen work. There we go. Or it could be one of these like groups at the end. So it could be, if you see the word sulfate, nitrate, and carbonate, you're going to have to, especially for separates, definitely for separates, you have to remember the formulas and the charges for these units. But if you can just remember that they're negatives, that will really help. Now, the rule is, if there is a halogen, okay, so that's your group 7. So what you do, you identify your 4 ions, and then you can go, yep, that's got a halogen in there. That's on my group 7. Whenever that is present, your halogen will always bubble off. That will be the gas given off. But if it isn't a halogen and it's like a sulfate, nitrate, or carbonate, oxygen will be bubbled off. Okay, and that is because of a process with the hydroxide ions, these ones here. What happens with that, it gets broken down and then it gets converted to water and oxygen. It's a bit of a long-winded sort of way of doing it. But if you remember oxygen, that's perfect. And then oxygen, remember how to test for an oxygen? Relight a splint, glowing splint, not just a plain splint. That would be like a miracle. That would be, that's be a glowing splint. Okay, so that's the rules for the positive anode. Okay, for the negative cathode, you are attracting your metals. Okay, so you, in this sort of side of things, you have to remember your reactivity series, and you're not always given that. Okay, so it's really important to try and remember the main parts of the reactivity series. But you've got to remember your cutoff point. So your cutoff point is where hydrogen is, and that's right, virtually right down the bottom. So there's only, the best thing to remember is what is below hydrogen, and that's your copper, silver, gold, and platinum. Okay, they're your 4 things that will do something different. So that is when the metal will be produced. So if you've got copper, silver, aluminium, or aluminium, copper, silver, gold, or platinum, you'll get a metal forming around the electrode. So for copper, it'll be like this lovely golden coppery color, very technical, and it will collect. Okay, but if it's above hydrogen, all you've got to say is that the metal is more reactive than hydrogen, So therefore, hydrogen gas is given off. That's it. That's all you've got to say. So for the cathode, let me recap. You need to know your reactivity series. You need to know where hydrogen is. If the metal in the solution is above hydrogen, hydrogen will bubble off because the metal is more reactive. If it is below hydrogen, it will be the metal will be collected. It won't bubble off. It won't be a gas. It will be a solid. So it will either drop to the bottom or it will collect around the electrode, basically. Okay. Keep it that simple. Okay. It might not sound simple, but definitely print off this slide and try and keep that to hand. Okay. Let me do that one. So that's the second part. So you've had electrolysis with just one solution, like lead bromide. You've had a situation where electrolysis has a solution with your water, with the extra hydrogen and hydroxide, and it follows these rules. Okay. And then you've got the final one, which is your actual required practical. I'm giving you a bit extra here to help revise with electrolysis. So this is a common diagram for aluminium and how to extract aluminium oxide from, aluminium from aluminium oxide. And there's a typical things that they always ask for this. Now, we don't have to worry about solutions because it will just be plain aluminium oxide. So that's all good. Okay, let me get my annotation up there. So here you just got to remember that aluminium forms a positive. Oh, there you go. Your oxygen is your negative. And as you can see, aluminium is actually 3+. It's in group 3. So that's 3+, and oxygen is 2-. Not that that really matters, but all you need to remember is that which one's positive, which one's negative. Okay. And then you just need to state that the aluminium will go to the negative. That's a cathode. And the oxygen will be attracted to the positive, which is your anode. Okay. Now, this is structured a little bit different. So you've got your cathode down the bottom here. So what happens is the aluminium, this is your aluminium here, will get attracted to the bottom and it gets siphoned off. Okay. Your oxygen will get attracted to your anode here, oxygen. But what actually happens, this is another question that will be asked. It'll ask, why does the anode erode away? I can't spell, I'm just not writing, my pen's not writing. Now, because these anode is made out of graphite, which is carbon, what actually happens, because there's such a high temperature, this is all happening really high temperatures at hundreds of degrees. Will you please work? The carbon actually, I don't know why it's gone red, mixes with the oxygen to form carbon dioxide. So there's a gas, that gas is given off, and that is your, that's why that anode erodes away. That's all you've got to say, because the carbon reacts with the oxygen, because it's at really high temperature, it forms carbon dioxide, which is the gas, and that bubbles off. Done. Okay. The next thing that always gets asked about this is molten. Okay, I've just said that this all happens at really high temperatures. Now, if my dog's coming in. Hello, Stella. Sorry. But aluminium oxide on its own has really, really high melting point. For electrolysis to work, you really need, well, it's essential that your substance is liquid, in liquid state. Now, as a solid, I'm saying its melting point is in the thousands. I can't remember, 2000 degrees, something like that. I can't remember off the top of my head, which is very unviable. It's very uneconomical. It takes lots of money and energy to melt it. So what they do, they mix it with cryolite. So here, molten, so dissolved in molten cryolite. That reduces the melting point down to around a few, like 800 or so. Okay, it just makes it a bit more viable, makes it more cost effective. All fabulous. So that's what you've got to say. You might ask, why is it why is cryolite added? It's just to lower the melting point, to make it molten. Molten just means it can move around. It's in a sort of a liquid sort of state. Okay, so that's another typical question always asked. Okay, I think that's about it for the aluminium with biopractical, to be honest. They're always the, why is that now not clearing? They're always the questions asked. Oh, okay, well, I've just added comments to that, and it's, actually I can do that, can't I? Oh, I've just remembered I can do that. Right, so this one here, this is the last combined science one. Okay, temperature changes in solution. It's really nice, quite a nice little simple one. It won't take that long, not like electrolysis. I did go overboard with electrolysis, okay? The required practical is just the aluminium bit, but you need to know the other bits as well to understand the practical, and electrolysis always is a tricky thing for students. So I'm hoping what I've explained has simplified it and given you the main points to revise. Right, okay, this one here is just identifying if something's exo or endothermic. So exo, it releases energy, it heats up. Endo, it absorbs from the surroundings, and the surrounding cools down. So these, for example, oh, I put them here, yeah. So your results here, these are your typical exothermic, so displacement, neutralization, they're both exothermic. I've just added here, decomposition reactions are endothermic. And I'm just going to add a bit of biology here. So exothermic respiration, endothermic photosynthesis. Now, as is known in biology, they're the same reaction, but flip around the other way. When you come to the Haber reaction later on in your module, some of you may have already done that already, plays a lot. In one direction, it's exo, in the other direction, it's endo, and it's the same thing for biology. Respiration, exo, photosynthesis, endo, it's all chemistry. So just remember that. So that might get asked, what is photosynthesis, is it endo or exothermic? So quick sip. Anyway, so this practical is really nice and simple. They just use they've done displacement here, or you can have neutralization. I've given 2 examples there. And it is just using a polystyrene cup. Why are we using a polystyrene cup? Insulation. It doesn't waste, it keeps the temperature. That's the important bit. You need to explain ways that the temperature is reduced from escaping. So having a lid on the top, wrapping it up perhaps with more insulation. You need to try and keep as much heat in as possible. Another tricky bit, let me just move my screen up here. To make it more accurate is your timings and your measurements. I think it's every 10, 20 or 30 seconds you take a measurement of the temperature and note it down, but obviously that will mean there's uncertainty or inaccuracy. You might not do it every 20 seconds, might be 25 seconds, that sort of thing. So there's lots of human error with this one, and lots of things where things can go wrong. But all you're doing, you're adding, you've got a certain volume of, I think they start with acid on this, and you add like 5 mils of alkali, stir it so that obviously everything gets mixed up. If you just pour it in and then do it, you might, you're not sort of mixing it all up, you're not actually making the reaction happen. So you've got to stir it gently and then measure the temperature, add more, 5 mils more, and then measure the temperature again. Okay, so it's a gradual thing, and you note down the temperature as you keep adding extra alkali to it. Okay, really there's not much to sort of say. That the main critical questions with this is, how do you stop or reduce temperature loss? How do you improve accuracy, like stop wasting heat? Yeah, then we'll probably go on about repeatability, calculating results and things like that. So really think on this one about the human error side of things. Okay, so that's all the combined science ones. And then the separate science for quite practical is this one, neutralization or titration. So I've thrown together some pictures here that will just summarize it. So what's the point of the practical? That's a very good question. It is all to do with working out the volume of an acid, or even like the concentration of an acid, based on knowing what your alkali is, basically, and the concentration of your alkali and the volume of your alkali. So it's working out the acid, or if you start with the acid, it's working out the alkali, or vice versa. Okay. I've put down indicators here. It's not just always litmus use. You could use alternatives to know what an acid and an alkali colour looks like. They might ask about increasing accuracy. So they might talk about meniscus. It's all about how you measure on your burette. Please make sure you spell burette and pipette correctly. So with the meniscus, you don't do it at the top, it's at the bottom of the curve. So that's another critical thing. I've added here risk assessments, like so your solutions and acids are irritants or toxic, that sort of thing, and how to do that. So these are all critical things that they will possibly ask along with the method. So I didn't actually put I haven't really put the methods in, but they can easily, if you want the methods, then they should be on the notes, the Save My Exam notes. These are all pictures from Save My Exams. Okay, I just didn't want to put them on the PowerPoint. It's going to be too much detail. But what I am doing with this one, I'm going to go through a question. Okay, a typical question, because the calculation side of things throws people basically. So what I have done. Oh, excuse me, I'm going to shut the door. There we go. Sorry, I need to make sure it's keep quiet. So I'm going to go through a question and typical things that you need to remember and structure when answers, and things to like remember. So a group of students decided to carry out a titration to find out the concentration. So I'm going to highlight that, the concentration of sulfuric acid solution. 25 centimeters cubed of sulfuric acid solution was neutralized by 34 centimeters cubed of potassium hydroxide. Can you see I'm highlighting and circling the data as I go? The concentration of potassium hydroxide was 2 moles per decimeter cubed. Right, instantly I'm going to annotate concentration equals mass over volume. And if you can't remember that, look at this here, look at the units. Moles, so that could be mass, or it could be moles. This is, moles are used in definitely for separates and higher separates, okay? So moles per decimeter cubed. Decimeter cubed is your volume. And remember that to go from centimeters cubed to decimeters cubed, you need to divide by 1,000. Okay, and then vice versa, you do times by 1,000 to go the other way. I don't know what that looks like. That's a centimeter cubed there. Okay, so instantly I've just got to jot that down, because I can see centimeters, centimeters, decimeters. I need to know how to convert that. Okay, so that's now out of my head, down on paper. I can relax a bit. So the equation for the reaction is shown below. That's fine. Okay. Right, for always with titration, with anything actually, chemistry, if you're given an equation, just make sure it's balanced. Okay, that is just a given. Always check. And if you don't know how to do balancing equation, or you need to practice, I have resources. I've got loads of examples, and I have my video as well on how I balance equations. So I'll quickly go sort of summarize, but what you do, you list all of the elements on either side, so KOHS, you number them and you count them, and then you balance them, and you end up with an equation like that. Okay, so we've now got that balance. And what I am going to do, can I delete? Erase? Yes, I can. Oh, I love it when the technology works. But yeah, if balancing equations is something you need to go over, just email me and I'll send you the video. Okay, and resources to practice. Okay, not a problem. So one, balance the equation. So I've done that. And must do that. I can't emphasize that enough. Name 2 specialized pieces of equipment required to carry out the neutralization reaction. This is where you need to know your spelling, the burette and the pipette. So remember double T's, basically, TTs. So remember that. Okay, burette, pipette. Also put in the wrong answer. Okay, calculate the number of moles of potassium hydroxide. So instantly I go, right, number of moles, right, I know that my concentration equals moles over volume. So I can rearrange that to go moles equals my concentration times volume. So obviously when you're writing out, make sure you write it out fully. Now, potassium hydroxide is here. It is potassium hydroxide, and it was 2 moles per decimeters cubed. Okay, so all you've got to do, I've written it down to save me calculating it. Oh, have I done that? Where have I put that then? Moles. Yeah. Oh, actually, what I'm going to be doing, when you've got an equation, what's really important as well is what I do. I add information underneath the equation. So I go back over the question. So I've got 25 centimeters cubed of sulfuric acid. So you should be able to recognize that H2SO4 is sulfuric acid. So what I'm going to do is on the side here, is like use this as a little table, like that. So we've got 25 centimeters cubed of sulfuric acid, and then we've got 34 centimeters cubed of potassium hydroxide. And we've also got the concentration of potassium hydroxide is 2 moles per decimeters cubed. Okay, so I'm just going to delete the pipette thingy. That thing there. Okay, I'm sorry it's gone over the writing, but this is what you've got to do. Okay, this is how I write it. So what I'd also put down here, moles and ratio. I don't know how you're taught about equations and using equations to work out different things, but I always make my equation into a table. I put my units down here, I take the information from the question and I put it underneath the relevant compounds, and then really helps you to visualize what I need to know, sort of thing. So what I need is moles of potassium hydroxide. So I use this. So I have concentration and I have volume, but your volumes have to be in the same units. So I'm aware of that. So it's centimeters cubed divided by 1,000. So it's actually, concentration is 2 times by 0.034. So therefore that equals 0.068 moles. So that's your first answer. And it's all there, all summarized, all visualized, and remembering my concentration as well, my equation there for concentration. So that's done, tick. Calculate the concentration of sulfuric acid in moles per decimeter cubed. So this part here, it needs the concentration. I actually box it, go, right, that's what I need to find out. Okay, now I know that this is 0.068, so I filled that in. So this is where balancing equations is really important. So you pick out your ratio. You've actually got 2 of the potassium hydroxide to 1 sulfuric acid. So it means you just halve it, 0.034 moles of sulfuric acid reacts with 0.068 moles of potassium hydroxide. So now we need to work out the concentration, which is the moles divided by volume. We have moles, which is 0.034 divided by volume, and that's 0.025 because we checked it's our units. We must always make sure they're in the same units. You do that, and I've written down the answer already. It's 1.36, so it'd be 1.36. Just checking, should be moles per decimeters cubed. And that's it. So always, 1, balance the equation. 2, show you're working out, please. You might get 4 marks for the correct answer if you just write that. But what if you get it wrong? But what if you got the equation right and you substituted everything, but it's just a calculation? You know, remember my escape method, it counts here. Write the equation, done. Substitute, yes, done. And I've checked for units, you know, moles per decimeter cubed, so it has been decimeter cubed. And then I've calculated it. So what if you got these 2 bits correct, but then when you calculated it, you got it wrong? You miss out on 2 marks. So that's why showing you working out is really important. I'm so sorry that's so messy, but hopefully that's given you some strategy on how to answer a typical exam question on titration. Okay, balance it, make it into a table, add the information underneath the elements, and then it just makes it so much easier, simpler to work out the calculations if you can. Okay, and then don't forget to show your working out. Very important. I think that's it. Oh, there's the answers as well for future reference if you need them. Okay, I think that was it. That's it. So, sorry it's gone on a bit. Shall I keep them? I'll keep them. Why not? Yeah, so it's been about an hour. I'm so sorry, but there was important bits to remember, and I've gone over an extra bit on electrolysis, which I really hope made some sense. But are there any questions? Was that okay? Was there anything else you need to ask me about anything that's cropped up? Nothing? You're all good? Don't forget, you must message me, email me if you need anything, okay? Especially those year 11s, mocks, go through those grade gorillas, keep going, do all of them if you want to, I don't mind. But just keep track of the scores, because I'm going to ask you what you got afterwards, like for the grade gorillas, to help fill gaps. So keep track, or you've got to do them all over again. Half equation. You know what? I find my brain's thinking now. What I have done, hang on, bear with, let me find it. I've got some other past paper, just like a really simple past paper question with some answers in this folder for this session. So there's that to do. But what I could do is write down some simple, the typical half equations for the typical elements used in electrolysis. Okay, let me make a note of that. Yeah, half equations. Okay, I will put something together in that folder. I might even Google it and find some images of like examples of half equations. Save me having to do it. I'm sure they've got it on Google, and I'll add it to that folder so that you can see the examples. Okay, good question. Like it. Okay. But yeah, that is no question. Let me just find the, hang on, bear with. I will find, I'm just going to open up chemistry, question paper, neutralization one. Right, let me share. Share. I can't find my bar now. Where's my bar? Share screen, that one there. So I've got in the folder as well. So I just, with some nice little simple questions on titration. I think it's only one long one that from maths and physics and maths tutor. Okay, so there's that as well to just sort of practice. But yes, I will also put together a photo or image of example half equations. Okay, so at least you can see them and visualize them and remember them. Okay, anything else? Really good questions. I like your questions that you come up with. Next time it's going to be physics practicals. Yay! Can't wait. Sorry, you can tell I love physics so much. No, give me biology any day. You mustn't have favourites, okay? Never have favourites. You love all 3 sciences equally, okay? Otherwise they get affected. Right, okay then. If there's no other questions, don't forget you can always email me anytime. But I will leave it there. I'm going to go to around my son's school for open evening this evening. But I hope everyone has a nice evening. enjoy yourselves, and I will be speaking to you soon, and that's it, and I'll see you next Thursday at 7 o'clock. See you later, bye.